All right, we are moving on to section 1.6. We are going to be looking at solving other types of equations. So far, the last few days, we've been focusing just on quadratics. All right, and we had the four techniques: factoring, square rooting, completing the square, and quadratic formula. Okay, but those are specifically for quadratics. We're going to look at what happens when we have higher powered things. All right, so we're going to solve polynomial equations, so things that involve maybe an x cubed or an x to the fourth, x to the fifth. We still can solve them by factoring. We're also going to look at solving some radical equations. Those would be equations that have some kind of square root symbol in them. And then tomorrow we'll move on to ones that aren't necessarily square roots. Maybe they have a cube root in them. Okay? All right, so we're going to start just analyzing a few equations that we do know how to solve. Our first one, we have 3x plus 5 equals 14. It's a basic linear equation. We would subtract the 5 and then divide it out. Okay? What is the degree of that question? 3x plus 5 equals 14. It's degree 1, right? We just have x to the first power. So degree 1 means it's linear, and we are just getting one solution. Our next one is degree 2. It's a quadratic. I'm going to subtract the 4 over. And that is factorable. Take a minute and look it over. See if you can pick out the correct factors. The 2x squared, we only have one option, splitting it into 2x and 1x. But the negative 4, we have a few options. Did you find one that worked? 4 and 1? All right. If we put the 4 here, 1 there, what signs do we need? Negative 1, positive 4. Check your insides and outsides if you were refoiling it. Does it get us a 7 in the middle? Yes? All right. So solutions on this one. From the first factor, we'd have a 1/2. From the second factor, a negative 4. All right. So this one was degree 2, and we had how many solutions? 2. First one was degree 1, we had 1 answer. Second one was a degree 2, we had 2 answers. Our third one is degree 3, so we should expect 3 answers. All right. This one, we are going to bring everything to one side again. That means I'm going to subtract the 4x, and I'm going to subtract the 4 over to the left side. This is factorable. What's the technique we had when we have 4 pieces, 4 terms? Yeah, split it in half. Do you remember what that's called? Grouping, yes. Factor by grouping. So if we group the first 2, what's common in the first 2 terms? All right, if we factor an x squared out, we are left with an x plus 1. What's common in the second 2? Yeah, we do want to take a negative 4 out. What's left over? And remember that grouping technique only works when the leftover part matches, right? So in this case, we had x plus 1 on both of them. So it's working. We refactor this now. X squared minus 4 becomes one of our factors, and then our common factor of x plus 1 is the other one. Can we factor x squared minus 4 further? Yes, that is a difference of squares pattern. X plus 2, x minus 2. So our solutions would be a negative 2, a positive 2, and a negative 1. I just went in the order of the factors. I don't really care which order you put them in. That's fine. Did we get 3 answers? So what you want to take away from this is the degree of your polynomial is going to tell you how many solutions there should be. Our solutions if we look at a graph, would show up as x-intercepts. So in my first one, I have a linear equation. It's going to cross the x-axis at 3. On the second one, we had a quadratic, a parabola. It's going to hit the x-axis at a positive 1/2 and a negative 4. Okay? Our third one, we have a cubic. Remember, the cubic ones have kind of that twist shape. So this one is going to hit at, if we looked at a graph, we've got -2, -1, and positive 2. All right? So we're hitting here, here, and here. So we're going to have a twisting type shape. Okay? I'm not going to have you graph all of these today, but I do want you to be thinking about when you look at those answers, what do they mean? On a graph, they mean those are my x-intercepts. Okay? The only ones that we are going to see on our calculator would be the real ones. If we come up with any imaginary solutions, we wouldn't see those. Okay? All right, let's go ahead and move on to some higher degree polynomials. All right, we are going to try to factor all of these, so we are trying to get a 0 on one end. So I am going to bring the 27x squared over to the other side by subtracting it. And then what's common that can be factored out? Take as much as you can. Yes, 3x squared. That leaves me an x squared minus 9, which is factorable into what? Good. That's that difference of squares pattern again. What's the degree of this one? Of the original problem? It's degree 4, which means we should be accounting for 4 zeros, right? When I look at this, I have a 0 here of 3. I have a 0 here of -3. What about here? It's just a 0, yes? My 0 is 0. But that's actually counting as 2 because it's an x squared, and either of those two x's could have been the 0. Does that make sense? We call that a double root. All right, it's degree 2, the x squared, so it's showing up as a double root. So even though I physically am only going to see 3 x-intercepts, I am accounting for 4 zeros. All right. Very quickly, do you guys remember what happens when you have a double root, what it looks like on the calculator? We talked about this other example that I have graphed in blue here. But if we were to graph this, we are saying we're going to hit at -3 and +3, and also at 0. The 0 was a double root. And what happens with an even root is your graph is going to touch there and bounce back off. It's not going to actually cross through. So if we were to analyze this whole thing, we have a positive leading coefficient. We have a degree that's even. Our arrows, our final arrows, should both be pointing up. We know we're crossing through the x-axis at -3 and at +3. And we know that we have to touch 0, but we have to bounce there. So we would end up with something like this, kind of a W shape. Okay? So the degree of the root, in this case a double root, tells me I touch and turn around. It kind of looks like a parabola right there at 0. Okay? All right, we won't graph all of them. Our next example, let's bring the 12x cubed over. Now what's common that I could pull out? Yes, 4x cubed. If I pull a 4x cubed out, what is left? X squared minus 3. Now, x squared minus 3. 3 is not perfect, right? So that's not a difference of squares pattern. We can still solve this, though. What's my zeros from the 4x cubed piece? 0. How many times is that going to show up? Yeah, that's a triple root, because any of those 3 x's that are in my x cubed piece, any of those could have been a 0. So this is a triple root It's going to account for 3 of my answers. How many total answers am I supposed to have? I'm supposed to have 5. So my other 2 have to come from this x squared minus 3. If I tried to solve this, figure out what makes it 0, I would be adding the 3 over, and then what? Square rooting, and remember when we square root, we have to account for both the positive and negative root. So my solutions are 0 and positive and negative root 3, but it does account for all 5 answers. Does that make sense? Yes, no? Okay. This triple root means that at 0, I would be crossing, because it's an odd root, I'd be crossing the x-axis, but because it's x cubed, I'm going to have kind of a cubic twist when I cross through, instead of just a nice straight line. All right. Next one. Again, we're trying to factor, so we're going to bring everything to one side. Okay. I am going to pause the recording. I want you guys to try factoring this by grouping. Checking those answers, you should have a positive and negative 2 and a negative 3/2. We okay with that technique? All right. Question 4, we're going to subtract the 81x to the other side. What happens when we try to factor out something common? What do we end up being able to factor out? Just a 3x. And what's left over? Okay. Now, x cubed minus 27 is a difference of cubes. We've been factoring differences of squares. Difference of cubes. We actually talked about sum and difference of cubes earlier this year, but I'm assuming we don't remember. So let's quick review. You might want to write this formula down at the bottom or in the margin somewhere. For sum of cubes, if we're trying to factor the sum of cubes, that would be things like a cubed plus b cubed. Okay, so you have 2 perfect cubes. There's a positive sign in between them. To factor it, you are going to get one factor that is just the roots. Same sign that you're given originally. We just take the cube root of a cubed, which is a. We take the cube root of b cubed, which is a b. We started with a positive sign in between. We're going to start with a positive sign in between. Okay, that's the first of the 2 factors. The second factor ends up being a trinomial. And the pattern is we square the first term. So we're going to square the a. We do the opposite of the product. Okay, the opposite of the product. The product of this would be a positive a times b. We want the opposite of it. And then our last term we square, so b gets squared. And that is a trinomial that is not factorable. If it were factorable, we'd have a different pattern for you to memorize. Okay? So we can factor it into a binomial and a trinomial. The only thing different when we have a difference of cubes is our signs. So we start out with a cubed minus b cubed. It's going to factor into a minus b, so same sign that we start with. And then we have that same pattern. Square the first term, opposite the product, and square the second term. All right, so we want to use that technique, that factoring pattern, on, what did we have, x cubed minus 27? So we're going to get a binomial and we're going to get a trinomial piece. What are the roots? X and 3, all right? So we're going to have x minus 3, same sign that we start with. Our trinomial part, we square the first one. Opposite the product. If I do the product of x and negative 3, I get negative 3x. I want the opposite of that, so positive 3x. And and then square the negative 3, which comes out as a positive 9. What was the degree of this question? It was degree 4, so we should have 4 answers, right? The first answer is going to come from here. X could be 0. The second answer is going to come from this x. X could be a 3. The other 2 answers are going to have to come from this quadratic, but it is not factorable. There is a middle term, so square rooting isn't going to work. We could complete the square, but we'd end up moving the 9 out of the way and having to cut the 3 in half, which means we're going to have a fraction. So, since that gets a little messier, best option in this case would be just using the quadratic formula. All right, so to solve this one, we're going to use the quadratic formula. X equals the opposite of b plus minus square root b squared minus 4 times a times c all over 2 times a. And if we simplify that, what do we end up with inside our square root symbol? We have 9 minus 36, negative 27. How is that going to be simplified? Negative means it is an I, right? Imaginary. So we're going to have an I. How about the 27? How would we break that up? 9 and 3, so 3 root 3. All right, so we end up with negative 3 plus minus 3i root 3, all divided by 2. How many answers is that? Right, what I just wrote down. That is 2, right? One with the positive, one with the negative. So we have accounted for our 4 answers, but on a calculator, if we tried to graph this, we would only see the 2 real ones, the 0 and the 3. The imaginary ones would not appear as x-intercepts. Okay? All right. We are shifting to solving radical equations. The first one I'm giving you is our most basic one, just saying the square root of x equals something. How do we undo a square root? We square it. So simply squaring both sides, because whatever we do to one side, we have to do the other. Squaring both sides turns this left side into just x, and it turns the right side into 81. Now, directions say to check your answer. If we plug an 81 back in and take its square root, do we get 9? So it worked. All right, we would say our solution here is just 81. It is going to be very, very critical that you check your answers when you're solving these radical ones, because you will often get extraneous solutions. Okay. So our steps for solving radical ones, and again today our radical is just a square root. We will move to higher radicals tomorrow. When we are trying to solve for something that's under a square root, our first step is to isolate the square root piece. If we have to rearrange some terms, move them to other sides, we can do that. But whatever's underneath our square root, we want to have isolated. And then we can undo the square root by squaring it. All right, so the second step here, raise both sides to the nth power. We're trying to undo an nth root, and we do that by raising it to the nth power. Okay? Step 3, solve the resulting equation. If there are still radicals, you have to repeat steps 1 and 2. And if you look at the last 2 questions in our notes today, you will see that there's 2 separate radical pieces, which means we kind of have to work through this process twice. All right, we have to do one at a time. Step 4 says make sure you check all proposed solutions back in the original to see if they truly work. All right, so for the first one, I want to isolate the square root piece. So I'm going to subtract the 2 to the other side. It becomes an x minus 2 now on the right-hand side. And to undo the square root, we are squaring. So it cleans up the left side nicely. The square cancels the square root. We just have 2x minus 1. On the right-hand side, we have to be careful. When you take x minus 2 and square it, you don't get x squared minus 4. Right? That's a common thing students do. They just square the two pieces. When we square this, you have to picture taking x minus 2 times itself, right? If we were to FOIL that out, we are going to get a trinomial answer. There is that shortcut pattern. It's great if you remember it. I'd prefer you to use that. We square the first term. We do twice the product. So the product would be negative 2x. Twice that would be negative 4x. And then we square the negative 2. What we have created is a quadratic equation. We have an x squared in there. So we can use the same techniques that we've been using for the last week. Let's get everything to one side. Subtracting a 2x puts that as negative 6x. Adding the 1 makes that a 5. And now because I have a 0 on one end, I can try to factor that. How do we factor x squared minus 6x plus 5? I heard x minus 5 and x minus 1. Does that work? Yes? So my possible solutions are 5 or positive 1. All right. When you check them, you have to put them back in the original question. You can't use any of the steps in between. So we're going to plug them back in. I'm going to plug it in for both x's. So my original question said the square root of 2 times 5 minus 1 plus, what was that, a 2? Equals x, which is supposed to be 5. All right, does it work? 2 times 5 is 10. 10 minus 1 is 9. Square root of 9 is 3. 3 plus 2 equals 5. So that worked. If we try plugging a 1 in, we have 2 times 1 minus 1 under a square root plus 2, and it's supposed to equal a 1. Inside the square root, we have 2 minus 1, that's 1. Square rooting 1 is 1. 1 plus 2 does not equal 1. So this does not work, which means the x minus 1 is extraneous. We would not include it in our answer. My only solution would be the 5. Now, it is possible, when we get these two answers, it is possible that we have both answers work. It's possible we have both answers not work. It's possible we have one work and one not. You have to check them. All right, let's try another one. First step would be to do what? Subtract the 3 over. Okay? Then how do we undo the square root? All right. If we square both sides, we end up with an x plus 3 on the left. How about on the right? I heard x squared minus 6x plus 9. Okay? We want to move everything to one side, so I'm going to subtract an x over, and I'm going to subtract a 3 over. Factoring it, very similar to the last one, we're going to have x minus 6 and x minus 1. So possible solutions are 6 and 1. All right, trying the 6. If we put a 6 in here, 6 plus 3 is 9. Square root of 9 is 3. 3 plus another 3 gets us 6, which is what we were supposed to get. Yes? So 6 works. If we put 1s in there instead, we have 1 plus 3. That's 4. Square rooting makes it 2. 2 plus 3 does not equal 1. So our 1 doesn't work. Our 6 does. For the next one, we have a couple options. I could subtract that single x over to the other side, but that leaves me a negative in front of the square root, and then I would have to divide that negative out. Okay, so it's kind of a two-step process. My other option would be to add the square root piece over to the right and subtract the 1 back over to the left. Either one's going to get me the same answer. It's going to take 2 steps, or 2 things have to move. Okay? So if I add the square root over here and I subtract the 1 back to the other side, I should end up with that. X minus 1 equals the square root of x plus 11. All right, I'm going to pause the recording. I want you to go ahead and solve this the same method we've been doing. All right, let's check our work. Did you plug both of them back in? Does the 5 work? Yes? Does the negative 2 work? All right, so we would leave negative 2 as an extraneous answer. We would not include it. Our only answer would be 5. All right, we're going to do one more quickly of that type before we move to the ones that have 2 roots. First step would be to add 3 to the other side. If I add 3 over here, I end up with just x minus 6. Squaring both sides, I end up with x equaling what? Good. X squared minus 12x plus 36, all right? If I subtract this first x over, I end up with 0 equaling x squared minus 13x plus 36. I need factors of 36 that add up to 13. All right, so we're going to have x minus 4, x minus 9. All right, so possible solutions, x might be 4 or x might be 9. If I put the 4 in there, square root of 4 is 2. 2 minus 3 is negative 1. That's not what I'm going to get on the right side. Okay, so 4 doesn't work. Plugging a 9 in, the square root of 9 is 3. 3 minus 3 is 0. On the other side, 9 minus 9 would also be 0. So 9 works. All right, so the trickier ones. General suggestion is to look at the 2 square roots and decide if one looks a lot more complicated than the other, eliminate that one first. All right, deal with that one and get it cleaned up right away. In this case, both of them are about the same. X plus 5, x minus 3, doesn't matter. So what we want to do is we want to isolate one of them. So I'm going to, I'm going to add the second square root to the other side. So I will have the x plus 5 under my square root on the left side. On the right-hand side, I have a 2, and I'm adding the square root of x minus 3. Be very clear that that's not 2 times the square root, it's 2 plus the square root of x minus 3. Okay? Our next step was to square both sides, which on the left cleans it up nicely. On the right side, it makes a mess, but we'll clean it up eventually. So on the left side, squaring the square root leaves me an x plus 5. On the right side, remember when we are squaring, we're timesing it by itself, or we're taking and using that pattern, right? The pattern says square the first term, so 2 squared would be 4. Then it says do double the product, twice the product. Well, the product would be 2 times the square root of x minus 3. Double that makes 4 times the square root of x minus 3. And then the last step is to square the second piece. Well, my second piece is this whole thing, right? The square root of x minus 3. If I square that, it just gets rid of the square root symbol. I'm still going to have an x minus 3 left. Now, it looks messy. We can clean it up. We have a 4 minus 3, right? Here and here. 4 minus 3 is 1. Can I subtract that 1 to the other side? Yes? Subtracting 1 over here leaves me a 4. I also have a plane x right here. Can I subtract that over? And since I only had one x over here, when I subtract it over, my x's are gone. The only thing left on the right-hand side now is the 4 times the square root of x minus 3, that middle piece. Okay, so it looks messy for a minute. It does clean up. Your next step, because remember, we're trying to repeat this process, right? Isolate the square root so we can undo it. My next step would be to divide the 4 that's in front of my square root out of there. If you can at all possible, if it's at all possible to do that, you want to do that. Get rid of that number that's in front of your square root. In this case, it's possible. I can divide both sides by 4. All right, the left side now becomes just a 1. The right side just becomes the square root of x minus 3. And now it's a question like the ones we've been doing. Okay, we can clean it up, squaring both sides. Squaring a 1 still leaves me a 1. Squaring over here leaves me x minus 3. And then I simply add 3 over. So I'm getting a solution of x being 4. We do have to check it. So let's put a 4 in here for our x. 4 plus 5 is 9. Square root gets me 3. 4 minus 3 is 1. Square rooting is 1. 3 minus 1 is 2. Works? Okay. Our last one is a little bit messier. We do have one square root. It has a 3x plus 1. That looks a little more complicated to me than an x plus 4. So I'm going to isolate that one first. I'm going to add this piece over to the other side. So I'm going to have the square root of 3x plus 1 equaling a 3 plus the square root of x plus 4. My next step is to square. On the left side, I end up with 3x plus 1. What do we get on the right side? Go through your pattern. What's the first piece going to be? Square the first term. What do we get? 9. Then what's the middle piece? All right, we want to double the product, right? The product would be 3 times the square root of x plus 4. Doubling it gets me 6 times the square root of x plus 4. And then I square the last piece, which leaves me what? An x plus 4. Okay. Let's clean this up a little bit. 9 plus 4 is 13. So we have a 13, we have an x, and we have a 6 root x plus 4. All right, let's move what we can to the other side. I'm trying to isolate that square root that's left. So subtracting an x over leaves me 2x. Subtracting 13 over leaves me negative 12. And here's why I said this one is a little bit messier. Because my next, in the perfect world, my next thing would be to divide out the 6. But looking at the left-hand side, can I divide both of those terms by 6 without creating fractions? No. Is there anything I can divide by? I could divide a 2 out of everything. So let's go ahead and divide both sides by 2. Even though it's not going to eliminate everything in front of my square root, it will help. What do we have on the left side? Okay. On the right side, the 6 and 2 reduce down to a 3. So again, I'm still stuck with a number there, but it is going to help because my next step, I have to square both sides. And squaring x minus 6 is a little easier than squaring a 2x minus 12. Right? I just have some smaller numbers to work with. So squaring on the left, we have x squared minus 12x plus 36. What do I get on the right side? This is a product, right? 3 times the square root of x plus 4. So when I square a product, I can square each part separately. I can square the 3, it becomes a 9. I can square the square root, which cancels it. But remember, it is a product. So it's not 9 plus the x plus 4, it's 9 times the x plus 4. Okay? Which turns into 9x plus 36 if I distribute. Let's move everything to one side. So let's subtract our 9x over. Subtracting 36 makes that constant leave. We end up with just x squared minus 21x. How do I factor that? Take an x out. What's left? Okay. So my possible solutions, x could be 0 or x could be 21. And we would have to double check those back in the original one. We're short on time, so I'll just let you know the 0 does not work. The 21 does. All right, so for homework, you are going to do 1 through 27 odds. I'm giving you the odds so that you can be checking your work. Obviously, there's quite a few steps of work to show for each question. I do expect to see that on your homework. Let me know if you have any questions.